So, good morning to everyone. Today I'm going to make a few notes during this session about the potential application of logical argumentation. In some cases I will be rather brief, pointing to further information in the literature. So if you lose me at some point or just fall asleep, don't worry. Just wait to the next note and then you will be back on track. Okay. The first note is about extended expressive power. So remember from yesterday that we could have considered several options about how we can extend the expressive power of the frameworks. One of them was to make a distinction between premises, strict premises, and a defeasible one. Another option was to add priorities, to make preferences among formulae. And now I want to consider another possible extension, which is switching from sequent to hypersequent. And let me first justify why we need to switch from sequent to hypersequent and then explain exactly what hypersequent are. Okay, so the motivation for this extension is the following. Remember that the first thing that we have to do is to decide about the basic logic. Okay, so in some cases, we might choose logics like S5 or the relevant logic RM, or get the intermediate logic MC. And in those cases, the problem is those logic, we don't know any, we are not aware of any cut-free sequent calculus from these logics. What does it mean? It means that it might be the case that for deriving conclusions in those logic, we might need the cut rule. Okay? The cut rule means that if we derive some lemma from a set of assumptions, then we can use, and we use the lemma for deriving new facts, then we can forget about the lemma and just have this conclusion. The problem with the cut rule, as you may know, is that these lemma exactly they are introduced in the proof, and it is not always clear how to obtain them. Okay? In particular, if we are enforced to use the cut rules, then we might lose the subformula property, which means that we, for the proof, we should look about subformulas of the premises. In case of argumentation frameworks, this is a bit problematic because this means that for constructing counter-argument of an argument, it might be not enough to consider only the subformula of the arguments. It might become more difficult to produce sub-arguments, and so the search space may be largely extended. So it would be nice if we could derive cut-free sequent calculi also for those logics in case that we are using them. And for this we need what is called hypersequent, because then we can construct, it is known that there are hypersequent calculi which are cut-free for those logics. Okay, what are hypersequent calculi? So hypersequent calculi were considered by several people. It was extensively investigated by Unicamp. And in principle, this is a finite multiset of a sequence. Okay, so we just take several sequences, each component consists of sequence, and the idea is to think about a hypersequence as a disjunction of sequence. So the bar here intuitively represents a kind of disjunction among the sequence. And then argument instead of being sequence, they are now derived hypersequence. Of course, once we switch to hypersequence, we accordingly have to change the sequent calculus to hypersequent calculus. So we have to adapt to new inference rules, etc., that are appropriate for hypersequence. How we do it? Usually it's very simple. We just for many inference rules, what we only need to do is to take the standard rule, for instance, from LK, or the standard sequent calculus for the system, and add to it the side sets of sequence. Okay, and this becomes a hypersequent rule. And similar with the other connectives, and we can take the additive versions of the rules, in which you see on the left-hand side we have the same set of assumptions, or the multiplicative versions of the rules. So the red part of this rule is the standard sequent calculi rule, and we just have to add here the additional sequence that might be part of the hypersequent rule. And also we have to take care of internal and external structural rules. So for instance, we should allow internal weakening in some case, from in the left and in the right. So we can add conclusions to the left-hand side and the right-hand side of the sequence. These are internal weakening internal rules because they are related to a specific sequence. And we also can have external weakening rule, which simply allows to add another sequent to the concluded hypersequence. And there are some additional rules which are specific to hypersequence. For instance, in some cases we will need what is called the splitting rule, which allows us to split. You see, we can split the original sequence to two new sequences that consists of fragments of the original sequence. And this allows us to produce new proof systems for hypersequence. For instance, this is a hypersequential variation of LK. Okay, we just take the usual rules of logical rules for the connectives in LK and turn them to hypersequential rules as I described earlier. Add new structural rule, internal and external ones, and then we are obtained with a new sequent calculi. And as I said, in case of S5 or LC, etc., those sequent calculi are cut-free. Okay, here is the sequent calculus, a hypersequent calculus for HS5. Is exactly extend the sequent calculus for S5 to hypersequent calculus for S5, which is cut-free.
Question.
Yes.
Why do you need the splitting rule in the previous calculus?
Exactly, this what would allows you to obtain those special property that you don't have in.
You cannot drop it.
You cannot drop it. You need it. Yeah. And it is discussed in more details in the papers that, in fact, introduce those calculus. Okay. Okay. Of course, we also have to change the attack rules, okay, to adapt them to hypersequence, okay? So suppose that we have this hypersequence and we want to represent rules that H1, hypersequent 1, would attack hypersequent 2, then we need to update undercut to undercut for hypersequence. Similarly, the rebuttal rule and consistency undercut, etc. So you can check that these are conservative extension in the sense that if n here and n here is 1, like ordinary sequence, then we immediately get the usual attack rules. Okay? So now we can define hypersequent-based argumentation frameworks just as before. Okay? Instead of using sequence, we can use hypersequence using the hypersequential calculi, but now they are cut-free. Okay, so we can more easily produce those arguments in case of S5, LC, RM, etc. And we just have to change the set of attack rules accommodated to hypersequence. And from now on, we can use the machinery that I described in the previous session. We can use Dunk semantics, etc. What are the benefits? Okay, let's start with the weaknesses. One weakness is that, of course, we are dealing with some more complicated structures and more complicated calculi. Okay, this is obvious. What are the benefits? Two main benefits. One of them is, as I said, cut elimination is guaranteed for more settings. Okay, so if we are working with a base logic to which no cut elimination calculi is known, then we might consider switching to hypersequence. Another benefit is related to the consistency of extensions conclusions. So in some cases, and I will come to this back again when I consider properties of extensions and properties of the entailment relations, maybe today or tomorrow, we will see that in some cases, extensions may not be consistent, although they are complete extensions. Okay, so conflict-free, admissible, complete. In some cases, they still may be inconsistent. But once so there are several ways to resolve this. One way to assure consistency is to switch to hypersequence. And then let's see an example. Okay, so suppose that we have classical logic with the defeat rule, and this is the set of assumptions. And this is a part of the argumentation framework that is obtained in this case. So note that this is one of the stable extensions in this case. Okay? However, so you see it cut free, no two arguments attack each other, it's admissible, and in fact it's stable and preferred because all the argument attacks the arguments that are outside the set. Still, this extension is not consistent. Why? Look, it consists of A1, according to which we can derive P, A2, according to which we can derive Q, and A3, according to which we can derive not P or not Q. So it's a little bit problematic. Again, there will be ways to resolve this, but one way is to add hypersequence. So we may switch to hypersequence using what I showed you earlier, HCL, the hypersequential version for LK, and then we get new hypersequence. For instance, we get H9, which is obtained by splitting A8. Similarly, H10 is obtained by splitting A7, etc., etc. Okay, we get new arguments, hypersequence. And now we get well, a more complicated framework. The solid lines are those of the original, no, sorry, the dashed line are of the original framework with sequence only, and the solid lines are those that are added because of the hypersequence. What happens now? So look, that was the previous extension, which was inconsistent. Okay? So A, 1, 2, 3, 4, and 5 is an inconsistent preferred and stable extension of the sequent-based framework. However, it is not admissible now. Why? Because there is a tag from H11 on A3, which is not defended by the set. Okay? Once we switch, we add this new hypersequence, we get a new extension, which is classically consistent. And as I will show you later, this is not a coincidence. Okay, second note. This note is about the ability to perform abductive reasoning in logical argumentation. Why abductive reasoning is important and useful, or in general, why these kind of approaches are useful. The main reason is that abductive reasoning with logic-based argumentation provide explanation to inferences and decision. So this is what is called, is part of what is known explainable AI, which is a huge area and a very extensive research topic nowadays in AI. Why? Because the new approaches, mostly those that are based on machine learning, etc., they provide very interesting outcomes. But the problem with those systems is that we cannot explain the outcome. Okay? We don't know why they produce this. It's very, in many cases, it's very rational and a beautiful outcome in case of pictures, etc., etc. But we don't have way to explain how they produce this outcome. Okay? And so it's very important and nowadays in AI to provide systems that, to define systems that can provide explanations to their outcome. And a sub-area of explainable AI is explainable argumentation, which is also a very lively research area in the context of argumentation theory. And abductive reasoning is just, the purpose of abduction in general is exactly that, okay? Abduction is the process of deriving set of explanation of a given observation relative to a set of assumption, okay? So we have a set of assumption, we have some observation, but the assumption, we have to extend somehow our assumptions in order to explain the observation. Okay, this is basically, very generally, abductive reasoning. Okay, so we say that sigma explain psi according to some entailment relation in the presence of the observation S, if, first of all, we usually require consistency of the explanation, the conclusion does not follow from the observation themselves. However, it does follow from the observations together with the explanation. Okay, this is abductive reasoning.
This is fantastic. System.
Yeah. So we want to adapt this idea to argumentation theory. Okay? How can we do this? Very simple. Okay? We have an argumentation theory. We say that a set of argument is a skeptical or credulous external abductive explanation of psi. Why external? Because I will give you another approach which is called internal explanation. So it's an external abductive explanation for psi relative to a set of assumptions if, first of all, again, consistency. So this set of argument should be consistent with respect to the base logic. Second, psi should not follow neither skeptic or credulous. So it depends on what ground we are. Okay, so if you use skeptical or credulous reasoning, so it does not follow according to the appropriate reasoning from the framework, but however, it does follow from the framework that is based on the set of assumptions, the base knowledge base together with the explanation. Here is an example. Okay. So again, we are in classical logic. And suppose that we are using the fit, and these are the set of our assumptions. This is the knowledge base, okay? So we know that the sky is clear, it is rainy. If the sky is clear, then it should not rain. Rainy means that the sprinklers do not work. Raining also means that the grass is wet. And if we have sprinklers working, then the grass is also wet. This is the set of our basic assumption. Now we want to construct an argumentation framework out of it. This is the part of the argumentation framework, as you can see. So we have several sequence of arguments out of this set of assumptions, based on this set of assumptions. For instance, if we know that it is rainy, and since rainy implies that the sprinklers do not work, then we conclude that the sprinklers do not work, and etc., etc. And once we incorporate the fit, then we have two stable extensions in this case. According to one, the sky is clear and it does not rain. And according to the second one, it is rain, and so the grass is wet. So two situations, each one of them is represented by a different extension. Suppose that we would like to make wet grass a credulous conclusion. So here, wet grass is suppose we want to make it a skeptical conclusion. And according to this framework, wet grass is only credulous conclusion. Why? Because it follows only from these extensions, according to this scenario. But according to the other scenario, the grass is not wet because we cannot conclude it here. Okay? What do we have to do in order to make this conclusion, wet grass, skeptical one? So the grass is always wet. Okay? This is our evidence. Okay? We know that the grass is always wet. How can we change this set of assumptions or word in order to accommodate to this observation? Okay, so one thing that we can do is add an explanation that the sprinklers are working. And this would explain, according to the other extension, and the wetness of the grass. So we have two extensions now. According to the first one, it's still raining and the grass is wet because it rains. But now, once we add sprinklers, this new assumption, we can conclude that the grass is wet, okay, also in the other extension. So it becomes an skeptical conclusions of our system. Okay? In order to implement this, we just need to add some postulates or properties according to the property that we have described earlier. So we need consistency, we need non-idleness, meaning that psi does not follow from the original framework, And sufficiency means that after adding this new explanation, side does follow from the new argumentation framework. Usually this is not enough. Usually we have to add some additional assumptions, like for instance non-vacuity. So we don't want that the new idea, new explanation would explain itself. Okay, one option would be just to add to the previous example, the grass is wet, as one of our assumptions, and by this resolve the problem. Okay, we don't want to do this. Okay, so we don't want to have self-explanation, and sometimes we also add minimality for assuring the conciseness of the explanation. So it won't contain irrelevant information. Okay, let me briefly describe an alternative approach to abduction. So this was an external approach in the sense that we just externally add new assumptions to our system. We could apply another approach according to which everything is done within the system. Okay? So all the considerations, the principle regarding the derivation of the abductive explanation are expressed internally in terms of attack rules, etc. How can we do this? Okay, here is the extended expressivity. We may do this by adding a special types of sequence. We call them abductive sequence. Okay? So in addition to the regular sequence, we also add these kinds of sequence. Note that the arrow is reversed deliberately. Why? Because we know this conclusion, and we want to do some kinds of reverse engineering and add to extend the support set with a new explanation that would entail the conclusion. Okay? The psi here may be inferred from gamma, assuming that sigma holds. Okay, in our previous example, here is an example of such an abductive sequence. Okay, we know that the grass is wet. The only thing that we know is that in general, sprinklers implies wet grass. We need to add this assumption in order to derive the conclusion. Okay, now we have new types of sequence, new types of arguments. We have to deal with them in the system. So we need new inference rules and new attack rules. How we produce those new kinds of sequence. So we have the abduction rules, meaning that if we know that gamma and sigma implies psi, but only gamma is part of our assumption, and sigma is not part of the assumption, but we still know that this is a valid implication, then we can derive this abductive sequence. Okay? Also, we have to add attack for abductive sequence. So, for instance, abductive defeat means that, as before, here we have the attacker. Now the attacked sequence is an abductive one, but we still can defeat it once the conclusion of the attacker implies the negation of subset of the attacked argument. But this time, the attacked argument is an abductive sequence. Okay, as a particular case of this abductive defeat, we get the consistency of the explanation. So the explanation cannot be inconsistent. If they are inconsistent, as we see here, the abductive explanation is eliminated. And we can also represent the other considerations: non-vacuity, non-idleness, minimality. inside the system by using attack. So this is a demonstration in the context of adaptive logic, but it could be applied elsewhere to the fact that we can use, we can express many considerations by attack rules in the argumentation framework. And now we have adaptive argumentation framework, which is again the same structure, together with new kind of arguments, adaptive arguments, and together with the new rules for adaptive arguments. Okay, here is a part of the argumentation framework that is obtained in this case. Note that here, for instance, we add internally the assumption that sprinklers the sprinklers are working. Okay, and then we get as an argument, not outside, not in our database, but as an argument in the system that the grass is working. And now we can define what is an internal adaptive explanation. So sigma is an internal adaptive explanation of psi relative to a set of assumptions set, S, if there is a subset of our assumptions such that this abductive sequence, skeptically or critically, depends on what you prefer, follows from this abductive argumentation framework. So this is another approach for abductive reasoning, and here I present the new argumentation framework, adaptive-based argumentation framework, and we can see that wet grass again is a skeptical conclusion of S, justified either by that it's rain or by the internal explanation that the sprinklers are working. A very quick result that relate the approaches so this theorem, I will just intuitively describe it. It says that in some cases the approaches are equivalent. Okay, some cases, but because, well, maybe this theorem can be generalized, but what we have shown is that if we use classical logic and the explanation is a singleton, using these kinds of attack rules, then with respect to the ground and the preferred or stable semantics, something is an internal explanation, if and only if it is an external explanation. We can add other assumptions like non-vacuity and still preserve this theorem. However, the equivalence not hold in all the cases. For instance, if we add minimality, then in some cases we lose the equivalence. And here is an example, but I will just skip it. The slide will be online and you can check it. Okay, so let's skip the details and move to the next note. So third note. This note goes back to the basics. Okay, I would like to reconsider the representation of the argumentation, the ingredient of the argumentation framework. Okay, so I would like to go and reconsider the forms of the arguments, in particular in terms of consistency and minimality, and the forms of the attack rules. In particular, I would like to suggest alternative formalization of the attack rule, or how to accommodate the rules to the logic. We will see that there is a tight relation between the base logic and the attack rules that we should choose. There should be a similarity between those two factors. Okay, so let's start with the forms of the arguments. So recall from the second model that originally arguments were defined as follows. So they were just pairs, the support of the, so it's just a pair, well, this is the support, this is the conclusion, and only classical logic was considered, and the support was forced to be minimal and consistent. Okay, the rationality behind this is that, well, if you use consistent and inconsistent theories in terms of classical logic, we get into troubles. And minimality, the rationality for minimality is that we want to express in the argument only what is really needed for the conclusion. And we suggested another approaches, which says, let's consider sequence and worry only about the fact that the conclusion follows from the premises. This is the only thing. Let's leave the rest to the argumentation system. Okay? And what I'm going to show you here is that this approach is okay. It's a sound approach in the sense that indeed now we can realize that indeed we don't have to care in the definition of arguments about minimality and consistency, because if we use the right attack rules, this can be taken care of inside the argumentation framework. Okay, so we can extend to different logical languages, we can lift the minimality and the consistency requirements, and the arguments were as follows. First, it is not realistic to assume the minimality, for instance, because if we make argument in real life, we don't care about minimality in many cases. Okay? So our support for the conclusion is not always minimal. Also, if we write proofs, the important thing is that they should be valid, but they are not always minimal. Okay? Of course, there is another problem, the computational complexity. To verify, if we require minimality and consistency as part of an argument, we have to verify whether a given argument is indeed an argument. So we must check consistency, we must check minimality, and here we get a known complexity result in the case of classical logic. Not to mention other logic where it can be that this result can get worse. And of course, there are practicalities issues. And this is the main message, that we don't need it because we can take care of about this in the framework. Again, this result shows what is intuitively written, what is the intuitive explanation at the top of the slide. So argumentation with inconsistent support may not be filtered out. We don't have to filter them out, even in cases that the base logic is trivialized in the presence of inconsistency. So even if we are not using paraconsistent logic as the base logic, the entailment on top of it, okay, the entailment that is induced by the argumentation framework will take care of this explosive problem. Okay, instead, inconsistency may be tolerated by attack rules and argumentation framework. So basically what this proposition says, that if we consider two frameworks, according to the first one, consistency is enforced, and according to so this is the one in which consistency is enforced, and according to the other one, we forget about this requirement and just add appropriate rules that take care of inconsistency, like consistency undercut, etc., then we are safe. Okay, then we have the extensions are the same, which means that the entailment will be the same. Okay, and then a similar result concerning minimality. I don't want to get, you see, there are some technical definitions here about normality of the attack rules, etc. But again, basically, what it says that is that we don't really need the minimality considerations, and we can get along without these considerations by incorporating appropriate attack rules. Okay, but this, once we shift from the definition, from the requirements about argument to argumentation framework, it doesn't go for free. Okay? We do have to take care about the attack rules. We need to do some work. And this is the subject of the next issue. Okay? So, the handling of inconsistency and minimality in logical argumentation framework may be shifted from the argument to the attack rules, but the use of the attack rules should be taken with care, especially when the base logic is not flexible. Here are some examples. Recall consistency undercut, which means that if we have tautological argument, it can attack any argument which is based on contradiction, and then once we do this, the contradictory argument is eliminated. However, consistency undercut is useless in some cases. For instance, if the base logic is clean logic, we don't have tautologies there. Remember that in clean logic, the third element is non-designated. So once we assign to all the atoms of a formula the value bottom, the third element, the value of the formula is still bottom. So the value of the formula is not valid. So in particular, we cannot use consistency undercut if the base logic is clean logic. Similar observation is about LP, unless we add some implications to it. Let me consider another case study, and this, in this case, we incorporate LFIs as the base logics of our system. So suppose that LFIs are one of the LFIs is a base logic in our argumentation system, and we use the fit. Okay? This is a very general description of LFIs, but just for people who are not familiar with them, but this is not the case here. Let's consider this rule in the context of LFI. So in the classical case, it looks okay. It is justified because what if it says? If it says that if we have a conclusion that defeats some subset of the defeated arguments, in which in the sense that the conclusion of the attacker implies double error, so it implies a negation of support of the defeated element, the defeated sequence, then the defeated sequence should be eliminated. However, in LFI, defeat may not be appropriate. Why? Because according to defeat, not P, double arrows no P, and P, double arrow P, they attack each other, right? According to defeat. However, well, in LFI, maybe they should not attack each other. Why? Because, for instance, not P, double arrow, not P, may attack the sequence which mentions P only if we also assume that P is consistent, okay? So it should attack that sequence. Not this one, but this one. Okay? And conversely, P double arrow P should not attack just the negation of P in case of LFI, but it should attack this sequence instead. So, well, defeat is not appropriate anymore for LFI, which means that we have to be very cautious about the attack rules that we choose once we have a base logic. What should be a solution to this problem? Well, we should require that the attacker should attack the attacked sequence when the conclusion of the attacker together with the attacked support, they are inconsistent. Okay? They are not just the negation of each other. In LFI, it is not enough. They should be consistent. Which leads us to a variation of defeat, meaning called inconsistency defeat, in which the condition is a little bit revised. And of course, we can define full defeat. So in the ordinary defeat, we just attack a subset of the support. Here we attack all the support, or we can refer to the direct defeat, in which we attack a specific formula in the support. But we may have other alternatives that are suitable for LFI. For instance, suppose that you want to allow only attacks that are based on the consistency of the assumptions of the attacker. Okay, so in this case, for instance, this sequent should attack that sequent because the first sequent assumes that P is consistent, but we don't want the other attack. So this sequence should not attack that sequence. So the attack should not be symmetric. How this can be obtained? According to inconsistency defeat, it's totally symmetric. But now we can, for instance, add another condition to the attack. Not only that the conclusion entails the negation of the support, but also that the support of the attacker is consistent. Here is another variation. Attack based on the consistency conclusion of the attacker. So now we want that the conclusion of the attacker will assume consistency. Okay, so we want that this sequence, which assumes that P is consistent, should attack that sequence, but not vice versa. Okay, and moreover, note that this sequence, according to this new policy, should not attack that sequence. Why? Because this the attack here is not based on the consistency conclusion of the attacker. Okay, so we have many refinements. Okay, in this case, this would be the attack rule. And so on and so forth. Here is a third consideration: attack based on consistency assumption of the attacked. Sequence. So in this case, we want to attack. So for instance, P double arrow P should attack any argument or any sequence that assumes that the negated formula is consistent. But again, we don't want to allow the reverse attack. So this would be represented like this. So the message is that once we determine the logic, we have to be cautious about what we want to say with the attack rules. This brings us back to the minimization consideration. Note, let's consider again the first variation. Okay, so here we say that the attacker should attack the other sequence according to defeat, if he can defeat it, and also the support of the attacker should be consistent. So, according to this attack, we want that this sequence will attack that sequence, right? Because the first one assumes the consistency, it has consistent support. But note that for this sequence, for deriving this sequence, circle P is not necessary. So the support in terms of derivation, the support here is not minimal. Okay? Yet we need it in order to apply the attack. So here, minimization might be even harmful. Because then if we insist on minimization, some attack rules would be ruled out, or meaningless, or whatever. Okay? So there are some delicate considerations here, and I will come back to this later in the Okay, so now I have to go to the other part of this module. Okay, so this brings me to the fourth note, if I'm not mistaken, of this session, which is related to general properties of the entailment relations. And in particular, I want to discuss a little bit relations to reasoning with maximal consistency, and then a little bit about rationality postulates, maybe today or tomorrow. Well, it turns out that there is a strong relation between many forms of reasoning that are based on argumentation framework and reasoning with maximal consistent subset of the premises. And this has been realized in a lot of studies. Here is a reference to some of them. I will mainly concentrate on the first paper, on the results in the first paper, which has been published a few years ago in Logical Computation. And the idea is as follows. So what is reasoning with maximal consistent of the premises? So this approach goes back to the well-known 1970 paper by Lexner and Manor. They suggest a well-known form of non-monotonic reasoning, according to which we should consider, once the set of assumption becomes inconsistent set, we should assume its maximally consistent subset. In the following sense, so the set of the maximally consistent subset of a given set of formulae is the set of all the theory all the sets which are maximally consistent in so two conditions. They should be consistent according to the logic, and they should be maximal in the sense that if we add something to the set, it's no longer consistent. Again, by this approach, we may consider three types of entailments. Two of them are skeptical one, and the third one is credulous one. Okay? So, skeptical, let's call this strong skeptical entailment. So, according to the strong skeptical entailment, psi follows from S if we have to take the intersection of all the elements, all the intersection of all the maximally consistent subsets of S, and then take the transitive closure of this intersection, and if psi belongs to this transitive closure, then it follows from S. This is a strong skeptical entailment. Okay, but we may define a weaker version, like in argumentation, then we will relate them, of course. A weak skeptical entailment according to MCS, maximum consistent subset. First, take the transitive closure of each maximally consistent subset of S. So we take the transitive closure, and only then we consider the intersection. Okay, so in the stronger sense, we first take the intersection and then the transitive closure, and in the weaker sense of skeptical reasoning, first apply the transitive closure and only then consider the intersection. And according to credulous semantics, then, as usual, we just require that the conclusion will be part of one of the transitive closures, so it should belong to the unit of the transitive closures of the MCSs. Of course, as expected, we have that strong skeptical entailment implies weak skeptical entailments, because if something is in the transitive closure of the intersection, it obviously belongs to every transitive closure, then it is in the intersection. So, strong entailments implies weak entailments, which implies credulous entailments, but the contrast is not true. Let me show you why this is the case. Here is again very simple example. So we have a set, the usual almost trivial set S1, P not P and Q. We have two maximally consistent subsets, PQ and not PQ. Therefore, according to MCS, according to the skeptical approaches, we can conclude Q. Why? Because Q is in both sets, but we cannot conclude P and we cannot conclude not P because they are absent in one of those sets. However, according to credulous reasoning, which is much more liberal, we can infer Q and we can infer P, we can infer not P because they belong to at least one of the maximally consistent subset. Of course, we cannot conclude anything else, because they are not part of the assumption. So we cannot infer everything, of course, but you see that it is much more liberal than the skeptical approaches. Therefore, credulous reasoning does not imply skeptical reasoning. Yeah.
So this relation between that the set code, strong set code implies the weak set code, and then it's kind of increasing the acceptance. So you accept less.
Yes, exactly. But it doesn't work on the other way. To see why the two skeptical entailments are not the same, let's consider another example. So we have here S2, which consists of P and Q and not P and Q. Here again we have two maximally consistent subsets, P and Q, and which are obtained by taking each of the formulas here. And now the intersection is empty. Okay. Therefore, if we take the stronger sense of skeptical reasoning, since the intersection is empty, only classical tautologies can be inferred from S2. However, if we take the weaker version of the skeptical entailment, then we can infer everything that follows from Q. Why? Because, in fact, Q is in the transitive closure of each set. Okay? We can still infer Q from each set separately. Therefore, it's also in the intersection of those, their transitive closure. So we can still infer Q here according to the Q and everything that is in the transitive closure of Q. All these formulas are inferable from S2 according to the weaker version of skeptical entailment. So we don't have the other way around by comparing these two skeptical versions. Okay, so far for the defining maximal reasoning with maximal consistency. So what is the relation between the entailment by maximally consistent subset and entailment that are defined by induced by argumentation framework? So we have defined three kinds of entailment. two skeptical one and one credulous one with respect to maximally consistent subset, and similarly, we define similar entailment with two skeptical one and one credulous entailment with respect to argumentation framework. So what is the relation between them? Here is one case in which we can relate them. Later on I will show you a more general result, but for instance, if we take classical logic and we take direct undercut, then interestingly, for every set of propositional assumption, we have the following. First, if we consider weak and strong entailment, then we see that the entailment with respect to grounded semantic, preferred semantic, stable semantic, all the weak and the strong skeptical entailment, they coincide. All the semantics become the same in terms of entailment, and all of them are equal to reasoning with maximally consistent subset. In this case, okay? Similarly, with respect to weak skeptical entailment and credulous entailment. Again, the argumentation-based entailments are the same as the maximally consistent, the MCS-based entailment in this case.
Excuse me, but these were classical logic.
This one can, but we will show that it's also true for many other logics. I will.
So it's a collapsing.
In many cases, it's indeed, it's a collapsing. Exactly. Not in all cases, okay? But if we take direct undercut together with classical logic, we must be prepared that it's these three types of semantics collapse to the same one. And it is the same as that maximally consistent subset. Here is another case, okay? If we take classical logic, and now we don't, instead of direct undercut, we just take undercut or defeat. Remember that the difference here is that in this case we consider equivalences, and here we just consider entailments with respect to the support of the attack rule. Again, we get similar results with respect to weak skeptical entailment, strong skeptical entailment and credulous entailment. And for the weak skeptical entailment, if we again want to get similar result, we just have to adjust a little bit the structure of the assumption. So the assumption should be normalized in some sense, and if we take undercut in this case, we again get the similar result. Okay, let's consider another case in which we still want to consider consistent subset, but not necessarily the maximally consistent subset. Let's consider this case, okay? So we have S3 that consists of these two formulas, P and Q and not P. Note that again, the intersection of the maximally consistent subsets of S3 is empty, okay? Because we have two maximally consistent subsets, this one and this one. Their intersection is empty, so again, we get not only this, but also the intersection of the transit closure is also empty. Okay, so according to the two versions of entailment that are based on credulous semantics, the weak one and the strong one, we only infer tautological conclusions in this case, if we take maximally consistent subsets. However, in this case, it looks strange that we allow only tautological consequences, we would like still to infer everything that mentions Q. Okay? It seems intuitive because, well, Q is not very related. In some sense, it's related. So it's a philosophical debate. But some people would like to infer here Q and its transitive closure. Okay? This was the motivation behind the definition of Benfahad, Dubois, and Pratt of a variation of entailment relation, but which is based on a consistent subset, which are not necessarily maximal. Okay? So what the new entailment says, psi follows from S if there is some consistent subset of S that entails psi. Note that it should only be consistent, not maximally consistent. And there is no consistent subset of S that entails the negation of psi. Okay? And if we adopt this definition, then in this case we indeed can infer Q, okay? Because those two conditions are met in this case. This is the reference if you are interested in the paper. How can we capture these entailment relations in terms of argumentation frameworks? It turns out that we can capture it, although it is not based on maximal consistency. And for this, we just have to incorporate two other attack rules. We need consistency undercut. Remember that consistency undercut eliminates any argument that is based on inconsistent assumption. And defeating rebuttal. Defeating rebuttal refers to the conclusions. So if we have two arguments with negated conclusions, or at least psi1 implies the negation of psi2, because we are using here rebuttal and not defeat, then according to this rule, the attacked argument is eliminated. And one of the theorems shows that if we take classical logic together with these two rules, then again we are able to imitate within argumentation framework this kind of reasoning. But again, the price is that all the three types of semantics collapse, as Walter said, right? And this shows, well, very generally why it works. Okay, why if we take S3 together with these two rules, we get this argumentation framework. Again, we see that any attempt to derive not Q is attacked by tautological sequent. So any sequent that whose conclusion is Q is defended by this tautological sequence, and other arguments are attacked because they have conflicting conclusions. So we can apply the defeating rebuttal for this case, and we get indeed what is expected. So we can derive Q, but we cannot derive P nor H nor. One note, however, is that you should not get the impression that in every case argumentation-based reasoning is reduced to reasoning with maximally consistent subset. This is not true. We have some examples that show that in some cases we get different entailment relations. For instance, if we take, even in classical logic, okay, taking classical logic, undercut as in the previous terms, but now take naive semantics. Naive semantics, we call that naive semantics takes the maximal conflict-free subsets of the set. Okay? And, well, I'll skip the details. We can see that there is a naive extension of this set, which is excluded in the maximally consistent subset according to maximum. So in this case, we can infer this conclusion from S according to MCS, reasoning maximally consistent subset, but we cannot conclude it if we only use naive semantics. Here is another example. Again, take classical logic, undercut, but this time with stable semantics and the weak version of skeptical entailment. Again, we can see, okay, so we did here some results that follow from the characterization of stable semantics that I will show you later. We can see that, for instance, if we use this set of assumptions, then we have these stable extensions of that set. So the arguments of each side formula together with the union of these arguments induces one of the stable extensions of this argumentation framework, which is not allowed by maximally consistent subset. Therefore, again, we can infer, according to maximally consistent subset reasoning, this conclusion, because you see R1 and every pair among R1, R2, and R3 is allowed according to this set. Okay, we can take R1 and R2 or R3, or R1 and R3, and still get maximally consistent subsets. But this conclusion is not allowed once we take undercut with stable semantics and classical logic. Okay, so as you have noticed, the results so far are related to classical logic. We wanted to extend the result beyond classical logic, so we actually consider, instead of classical logic, any logic in which the following rules are admissible. Okay, we require reflexivity, cut, monotonicity with respect to both sides of the sequent, and the rules for introducing in both sides the negation and the conjunction. Okay, and single conclusion calculi, the phi here should be empty, and the delta and delta 2 should contain only one form, at most one form. Okay, so we consider all logics in which these rules are admissible, in particular classical logic, but others as well. And we divide the attack rules to three types. Okay, three types of attack rules. One type we call them the subset attacks, in which the set of attacks rule consists either defeat or undercut or both of them, so the intersection with defeat and undercut should not be empty. The direct attack, the second family, consists of attack rules which are either direct defeat or direct undercut. So according to the direct attack, we attack specific formula in the assumption. And the third family, the consistency-based attack, again, are direct attack, but together with consistency undercut. The attack rule that eliminates argument that are based on inconsistent set of assumptions. And by this theorem, we actually can characterize different types of semantics we can characterize the extensions according to different types of semantics. So, for instance, again, assuming that we have a logic that satisfies the previous condition and attacks, which is one of these three types, then, for instance, if we have direct attack or consistency attacks, or the attacks are of one of these two families, and we take preferred stable or semi-stable semantics, in this case, with respect to any logic as defined previously, we can say that the extensions with respect to these semantics consist of the arguments of each extension is in fact the arguments that are induced by one of the maximally consistent subsets of the assumptions. Okay? In case, so this actually is a generalized result with respect to other logics, not only classical logic, which shows that in this case, again, we have a collapse of these three types of semantics. For set attacks, the situation is a bit more complicated. We have a more complicated definition of the subset of S. So instead of taking the maximally consistent subset, we have to take a more complicated set, which is denoted omega. And in other cases, for the grounded semantics, we have other definitions. I will not get into the details here, but okay, so here we have some examples of how this can be obtained. But again, so by characterizing the extensions in each case, we are able, of course, now to characterize the entailment relations that are obtained by those semantics. Okay, so for instance, by the first item in the previous theorem, we get this item that shows that strong skeptical semantics with respect to any logic satisfying the conditions that I showed you in the previous slide, and with respect to attacks that are in those two families, and when we take these one of these three Dunked semantics, in all of these cases, we end up with reasoning with maximally consistent subsets, not only in classical logic. Okay? And there are many other cases that I will not describe here, but again, they follow from the characterization theorem about the extensions of the Dunked semantics. In any case, you see that in many cases, there is a tight relation between reasoning with argumentation-based entailment and some consistency considerations on extension or subset of the set of arguments. Okay, I will not go on now because it's almost 12. I will just one word about what I plan to do tomorrow. So tomorrow we'll do two things. First of all, we will consider rationality postulates. Rationality postulates are desirable properties of the entailment relation. Why we need this? This is a very common policy in AI to evaluate entailment relations or consistency operators with respect to rationality postulates. Why do we need it? Because once we want to set up an argumentation framework, we have a degree of freedom. We can choose different languages. We can choose different base logic. We can choose different Dunked-type semantics. We can choose different attack rules. We can choose different type of entailment relations, whether it's credulous or skeptical. So we have a jungle of entailment relations that depend on what are our basic choices. So how can we tune a specific argumentation framework for a specific purpose? We do this by analyzing some rationality postulates that in some cases show us how to choose. This is one thing that we will do tomorrow. The other thing is I will show you some proof systems for argumentation reasoning, argumentation framework. And the issue here is that unlike proof systems to ordinary logics, in which when you derive something you can count on it for later on, remember that we are dealing with non-monotonic entailment, which means that although we may derive something, we may later on change our mind. So the derivation is a tricky business. Not always we can rely on specific results of the prefix of our derivation for extensions of the derivation. So there is some delicate issues concerning proof systems for non-monotonic systems, and I hope to cover this also tomorrow. That's it. Thank you.
I have a question, a very broad question. Is it possible somehow to combine this framework with conditional probabilities? You know why? Because if you could do that, then you could sort of define some Bayesian networks, which could be explained.
Yes. In fact, there are some works, I can show you give you the reference, that combines argumentation framework with conditionals in general. So this is exactly their purpose, okay? To work with conditionals and apply to
Conditional probability.
yes. So sometimes so there are some work with conditional, there are some work with conditional probabilities. In order, of course, to incorporate Bayesian framework, I have not done work in that direction. I will not talk about this in this course, but there is plenty of work on this subject. Yes. Okay, thank you.